So in this video we will solve part of the two exams of June 2020. Remember that 2020 was a bit of a particular year because of the COVID situation, so there were two exams, one for a first group and one for a second group, and what you see over here is the exam of the first group. In this exam of the first group we'll solve question 1 and question 3, right? Question 2 is a theory question, so you should refer to the overall video course, and we'll solve question 5. Question 4, which is a two-stage simplex method question, is also a question of the exam of June 2019. So here's the exam of the second group, and in this exam we'll solve only question 4. As you can see, question 2 is again a theory question, so you should refer to the overall video course, and for the other questions they are left for your information and you can try to do them by yourself. Here are questions 1 and 3 of the exam of the first group. Both questions belong together. So the first question is find the local extrema, so minima and maxima, and the saddle points of the function that is given. Then in the third question we ask to apply Newton's descent method for this function and to perform the first iteration with a step size equal to 1 starting from the initial point 1, 2. So again, as usual, try to do this by yourself first and push the pause button. Let us first solve question 1. So the first thing that you have to do is to find the critical points, so the points at which the gradient is equal to 0. So the first thing that we have to do is to compute the partial derivatives with respect to x and y, and of course you should be able to compute a derivative and a partial derivative. So make sure when you come to the exam that you can take the derivative of the most basic functions, that you know the derivative of a product, and that you know, for instance, also the chain rule, right? And that you can compute indeed a partial derivative. If you go through the calculations, well, these expressions here are respectively the partial derivative with respect to x and the partial derivative with respect to y, so this is the gradient. If you set the partial derivatives to 0, well, you can see from the second equation that you have here two candidates for this part. X is equal to 0, but this is not a good idea because, well, the logarithm is not defined, and then you have y is equal to 0. Right, so we'll set y is equal to 0. This one is then equally 0. If you have y is equal to 0 over here, well, you have two possibilities to make the gradient with respect to x 0. It's 1, because the logarithm of 1 is 0, and exponential of -2. This will make this thing here 0. So two critical points, 1, 0, and a second critical point, which is the exponential of -2. Then you have to compute the second derivatives with respect to x, y, and the mixed derivative with respect to x and y. So take this one and take the derivative with respect to x, so this yields 2y. So this is the expression here of the Hessian. And to see if these critical points are maxima, minima, or saddle points, well, you have to evaluate the Hessian at the critical point. In this case here we have a diagonal matrix with 2's on the diagonal, so this is clearly a positive definite matrix. So this point here is a minimum. In this critical point, if you evaluate the Hessian, you will see that it is neither positive definite nor is it negative definite, so it's indefinite, so this point here is a saddle point. So now we have to apply Newton's method, right, with a step size of 1 and initial point here that is 1, 2. Remember that Newton's method, well, you have a descent direction that is minus the Hessian at the point you have arrived at, inverse, and then times the gradient at that same iteration, and then the update equation is xk plus 1 is equal to xk plus alpha k dk, and in our case here this is equal to 1, right? So we should use this, but at the very beginning. So in our case here, d0, you'll have to evaluate the Hessian in x0 and the gradient in x0, and this is what is done over here. If you plug the values 1, 2 in the gradient, this is what you obtain, and if you do the same thing in the Hessian, this is what you obtain. Of course, we have to compute the inverse of a 2 by 2 matrix. This is something that you have to be able to do because you've had a course on linear algebra. Here is this inverse, right? And then you have to compute d0 minus the Hessian inverse times the gradient in this point 1, 2. If you go through the calculation, this is d0, right? So x1 will be x0 plus alpha d0. Alpha is equal to 1. If you go through the calculations, this is the x1 you will reach, and this is the first iterate. And of course we can check this using the software that we have presented in the section on numerical optimization. We are using Newton's descent. Here is the function. The function here is in terms of the variables x1 and x2, but apart from that it's the same function. And here in MATLAB the natural logarithm is the function log, but this is indeed implementing an ln function, a natural logarithm. We set the number of iterations to 1, the maximum number of iterations, the step size to 1, that's alpha, and we start from the point 1, 2. If we run the code, here we have the initial point we start from, and after one iteration we obtain the first iterate, and this is indeed, well, 1/3, 4/3. So this is the next question that we will solve. It's a linear program. The first thing that you should do is write this problem in its standard form. Do not forget this, do not skip this, and then you'll be able to evaluate if it's possible to find an initial feasible solution. If this is not the case, you'll have to solve an artificial problem. Here again, write this artificial problem and clearly define stage 1 and stage 2. As usual, try to do this by yourself and push the pause button. First thing is to bring this optimization problem in its standard form. The maximization problem is transformed into a minimization problem. We simply take the objective function and multiply by -1. Here we have a -5, and when we apply the simplex algorithm, we request the b's to be positive. So what we do is simply take this second equation and multiply it by -1. This is what you obtain. Do not forget to change this inequality smaller or equal into one that is larger or equal. We have two inequations with smaller or equal, the first and the third constraint, right? So we'll have to use two slack variables, C1 and C3. Here we'll have an inequation with larger or equal, so we have a surplus variable C2. This is the standard form where x, y, z, C1, C2, C3 are positive or 0. It will be impossible to find here an initial feasible solution by just looking at this system. We can use C1 and C3 as pivot variables, right? Basic variables, because they appear only once in one equation, and well, the coefficient is positive. In the second equation we have a problem. C2 appears only once, but it has a negative coefficient, right? So what we'll have to do is add here an artificial variable C4 and treat this artificial problem, right? So we'll minimize a cost C4 with respect to these constraints. Here it's only necessary to add one artificial variable, since we have already pivot variables in the first and third equation. Do not add more artificial variables than necessary, otherwise you'll end up with an artificial problem that is more complicated. If this problem has a feasible initial basic solution, right, well, this problem will have a solution with the cost 0, which means that the artificial variable C4 will be 0. So we'll start by solving this stage 1 artificial problem. So let us start by writing the stage 1 artificial problem in the form of a tableau, right? And the basic variables will be C1, C3 and C4. Notice that the cost here has been written here below in the tableau, and we can see here that this tableau is not yet in its canonical form. We see that there are zeros below the pivot over here, zeros above and below the pivot over here, but here we have a problem because we have the pivot over here and there is a non-zero element over here. So what we'll have to do is a row operation to create a 0 below the pivot, right? And the multiplier will be the element to eliminate, divide by the pivot, so it's a 1. If we perform this row operation over here, well, this line will disappear. This is why you have this red line, and it will be replaced by this one over here. And in this line you find the reduced costs. As you can see, well, this one is negative and it's the most negative one, so we have not yet arrived at the optimum. So we know that y will enter the base and we need to find the variable that will leave the base. So this is why we compute this column. So it will be these elements divided by the corresponding elements in this column over here. So here minus 6, 5 over 2, 6 over 5. The smallest positive coefficient, right, is this one. If you want to know where this is coming from, well, this is coming from the step 2 computation of epsilon in the simplex method. This is explained in the video course. So we have now identified the new pivot, right, and we know that C3 will leave the base because this was the previous pivot. What we have to do is create zeros above and below the pivot, and we have to make sure that this pivot becomes a 1, right? So we'll have to use the following multipliers in these 3 row operations, and we'll have to multiply the third line by 1 over the pivot, so that's a 1 over 5. Well, if you do the elementary row operations that you see over here, this is the tableau you obtain. And in this tableau, if you look at the last line, you will see that this reduced cost is still negative. So we have not yet reached the optimum. We know now that z is going to join the base, and we have to find which variable is going to leave the base, right? So this is why we have this column in which we take the elements of this column and divide them by the corresponding elements of this column over here. So this one divided by this one, that's 18, this one divided by this one, that's 13, and this one divided by this one, that's minus 2. We take the smallest positive coefficient, so this leads to this one over here, and we have now, well, identified the pivot, and we know that, well, since this is the old pivot, that C4 will leave the base, which is good news, because this means that at the next iteration, when we have the tableau, we'll have, well, the solution of the artificial problem, and by definition here, since this one is going to leave, it will be C4 is equal to 0, which means that the original standard problem has indeed an initial basic feasible solution. So we have identified our new pivot. We should make sure that there are zeros above and below the pivot, and we should multiply this line by 5 to obtain a pivot that is 1. The multipliers are easy to obtain. As usual, it's the element to eliminate, divide by the pivots, and this is what you obtain. So when you perform these, well, row operations, this is the tableau that you obtain, and you can clearly see that it is the last tableau. We have this typical last line in which we recognize the costs, right? And we see indeed that the cost is equal to 0, and C4 is no longer a basic variable, so it is set to 0. This is the end of stage 1. We have 3 basic variables, y, z, and c1. This is why x is equal to 0. You can read the value of y in the tableau, of z 13, and c1 is equal to 2, and all other variables are equal to 0. Of course, at this stage you should look at this standard form and have a look if, well, with this solution we have met the constraints. So we have here 13 minus 9, yep, that's 6, so this one is okay. We have 18 minus 13, these ones are 0, so 5, this is okay as well. And then we have here 0, here we have 45 minus 39 plus 0, so that's a 6, so that's okay as well. So now we are ready to initiate the second stage, and in this second stage what we'll do is we'll leave out the artificial variable, and of course we'll cross out this last line because it has to do with the artificial problem. And what we'll have to do is write, well, the cost involved in our standard form, and this will be minus 2, 3, minus 1, 0, 0, 0, 0. So as explained before, this is how we initiate stage 2 with this tableau. You can see over here, or you remember that the basic variables are y, z, and c1. You can see that there are zeros below this pivot, but there is a problem in these columns here because below the pivots, well, you do not have zeros. So we do not have here a tableau that is in its canonical form. So what we have to do is to do row operations. So we have to make sure that these ones become 0, right? So we'll have to do row operations, and the multiplier to bring a 0 over here is this one divided by the pivot, so we have a 3 here, and here we'll have this one divided by the pivot, so it's a minus 1. If you perform the 2 row operations, you obtain a tableau in which this last line here this is why it's crossed out, is replaced by this line over here. These are here the reduced costs. They are all positive, so this means that we have arrived at the optimal solution. It turns out that this basic initial feasible solution that we have found using the artificial problem is directly the optimal solution. We can read it again from the tableau. X is non-basic, so it is 0. Y is 9. Z is 13. C1 is 2, and C2 and C3 are set to 0. This means that, well, in the original problem, in the equations, in equations 2 and 3, well, we meet them with equality, and this you can see because C2 and C3 are 0, and there is, in this case, because we have here a smaller or equal, some slack here because C1 is equal to 2. We can read the optimal cost of the minimization problem of the standard form. Well, you have to take this one and take the opposite, so that's 14. But the optimal cost of the original maximization problem, and this is what is interesting us, is minus 14. And indeed, well, if you take y is equal to 9, you'll have minus 27 plus 13. This is minus 14. So you should always make that kind of check and see that indeed your solution meets the original specifications. We will not do it because we have done it at the end of stage 1, and our optimal solution is also the solution that we had obtained at the end of stage 1. Let us now try to solve question 5. Use Lagrange's multiplier optimization method to calculate the shortest distance between the two parabola that are given over here. As usual, try to do this by yourself and push the pause button. Let us have a look at this problem. Let us define x1, y1 on the first parabola. So obviously x1 and y1 meets this equation. Similarly, x2 and y2 is on the second parabola, so the coordinates must obey this equation over here. We want to minimize the distance between the 2 points, and we have seen before that it is equivalent to minimize the distance squared between the points. This is simply because, well, taking a square, the square is a monotonically increasing function, and therefore the problems are equivalent as far as the minimizing arguments are concerned. So this is our minimization problem. We minimize the distance squared, and x1, y1 is a point of the first parabola, and x2, y2 is a point on the second parabola, and therefore we see those constraints. So this is typically a problem we can solve using the Lagrange multiplier method. So we have to construct the Lagrange function, right? So here lambda is a vector, lambda 1, lambda 2. So this Lagrange function is the objective function. Here the distance squared plus lambda 1 times g1, right? This is the first constraint, plus lambda 2 times the second constraint, right? We have now transformed our optimization problem that is constrained into one that is unconstrained, but with 2 additional variables, which are the Lagrange multipliers. So what you have to do is to compute the partial derivatives with respect to x1, x2, y1, y2, lambda 1, lambda 2, and of course these 2 partial derivatives simply yield the constraints. We have to set those partial derivatives to 0. So here you can obtain lambda 1, right, and you can inject it in the third equation. and this is what you'll obtain. And you can isolate here lambda 2 from the fourth equation and inject it in the second equation, and this is what you obtain. In both equations you can simplify here with the 2, and in the this equation over here you can change signs. And what you can observe here is that you have some symmetry, and if you set y1 is equal to x2, right, and y2 is equal to x1, you can see that the equations 7 and 8 become equivalent, right? And this is also the case for equations 5 and 6. So this is a bit of intuition, but you can see where it comes from. So this is the parabola x squared is equal to y minus 2, right? And this is the parabola y squared is equal to x minus 2, and you can kind of see that the minimum distance will occur somewhere around here, and you can see here that this parabola can be mapped on this parabola using an axis of symmetry. Y is equal to x, and at the points where you'll have the minimum distance, right, you can see because of this symmetry that indeed y1 is equal to x2 and y2 is equal to x1, right? So what we can now do is take these relations and inject them in equation 7, and if you go through the calculations you will see that you obtain this equation. Obviously x1 is equal to x2 in addition to these equations would simply yield a point that is the same. That is not possible, so we'll have here that this relation must hold and that x2 is equal to a half. x2 is equal to a half is equal to y1 by this relation over here. And what we can then do is, for instance, inject y1 in equation 5 and isolate x1, and this yields 9/4, and this is also the value of y2 by this relation over here. So we have the coordinates of the points x1 y1, x2 y2, right? So what we can do is inject this in this one, but we have to take the square root now because we speak of shortest distance, not shortest distance squared. So what we'll have is this term, but this term will be exactly the same. When you take the differences, we'll have the square root of 2 times 9/4, right? For instance, x1 minus x2 squared, and you'll have the same for the other one. So this explains the 2 over here, and if you go through the calculation, this yields 7/4 times the square root of